so much for the opportunity to share some thoughts on advances in asphalt pavement engineering. And I believe it's a timely topic because when we look at our road network, about 5% of the network has asphaltic surfacing. And as we improve our infrastructure, we tend to be shifting to the left of this plot where earth roads will be improved into gravel road, and gravel road will be improved to surface dressing, and then we'll be shifting to the left of that plot. So it means that if we are able to take advantage of advances in asphalt pavement engineering, we'll be able to develop a network of roads that perform long and they perform in an optimal condition. So when we take a cursory look on our asphalt roads, we have one common difference that we can't fail to recognize, and that is fatigue cracking. Others prefer to call it alligator cracking. It's a common difference that we see on our roads.
You are an academician, so.
All right. So what we see in the photo is another display of fatigue cracking on the N6 highway. We also see a lot of rutting on asphalt roads. And rutting, apart from structurally impacting the pavement, it also has safety implications because water can pond in the rut, and that can lead to hydroplaning, and that carries safety implications. So rutting is a very serious distress that we don't want it to happen on our road, or if it will happen quite later in the life of the pavement. So yes, we still keep on experiencing increasing traffic loading. And that means our pavement system is challenged. And therefore, there's the need to look for innovations to make sure that our roads are performing better. All right, so we can improve pavement longevity through 4 broad approaches. We can look at it from the design perspective. We can also look at it from construction perspective, where we want to make sure that construction quality is good. We can also look at it from management. And this is where the road agencies will come in. And then at a higher level, we can look at it from policies that the government will put in place. However, this morning's discussion is going to focus mostly on the design perspective. How can we improve our asphalt pavement performance through innovation in design? And on this point, I'll be looking at the binder, or what we commonly call bitumen in our part of the world. Then I will move on to the mixture, the asphalt mixture. And then lastly, I will touch on the structural design, the pavement thickness design. All right. So looking at asphalt binder grading, grading started in the 1900s with penetration grading, and it is a very simple test, an empirical test. We have a needle, we load it with 100 grams, and it is pushed into the bitumen at a temperature of 25 degrees Celsius, and we just measure what will be the depth of penetration after 5 seconds. A very simple test, but the issue is that it is not measuring any fundamental property of the bitumen, and also the long-term binder aging effects are not considered. So one major shortfall is that binders with the same penetration grade will perform or can perform differently in different environments. So that gave way to viscosity grading, where viscosity, as we all know, is a material property. It is stress over strain, so it's a material property. And viscosity grading, we do the measurement at 2 temperatures, 60 degrees and 135. Another major issue is that no viscosity measurement is done at the intermediate temperatures. And that is where fatigue cracking starts. And fatigue cracking is one of our major issues with our pavement here in Ghana and in most parts of the world. And so it's a major drawback with viscosity grading. And that's what we do here in Ghana currently. Long-term binder aging effects are also not considered. And another key thing is that with viscosity grading of bitumen, we can have binders that will have the same viscosity grade, and yet they can perform differently. And so with these shortcomings, the pavement community tried to do a lot of research to come up with a more robust asphalt grading system, and one that we know of is the superior performing asphalt pavement, commonly called SuperPave, which is a product of the Strategic Highway Research Program that was conducted in the US, and it ended in the mid-1990s. And the overall aim was to develop solutions, technologies that will combat the highway infrastructure deterioration that was happening in the US at that time, and to improve the performance, durability, safety, and efficiency of the highway infrastructure. That was the overarching objective of that research. And so the SuperPave system is outcome of that research effort. And the system has 3 components. We have the binder grading, we have the measure design aspect, and then the measure performance evaluation. And here, let me note that the measure evaluation component has not been widely adopted because of the complex nature of the testing equipment that was recommended by that research. So here in Ghana, we started making some efforts towards SuperPave, and when we check our standard specification for road and bridge works, we will see that we have some specifications on the aggregate quality, aggregate gradation, and compaction requirements. But that is where somehow we've ended, and we've not taken full advantage of this innovation. All right. So let me delve a little bit deeper into the SuperPave system. All right. So the SuperPave binder characterization, it is a performance-based system, and it is improving the previous one, the viscosity, and then the penetration grading system. So this is how it works. The physical properties of the bitumen will be measured over a range of anticipated pavement temperature. So we will look at low temperature, intermediate temperature, high temperature. The properties of the binder will also be measured considering different aging conditions that the binder will be subjected to. For example, during the construction, the mist production, the laying, then during the early life, service life of the pavement, the kind of binder aging that will take place, and also later in the service life of the pavement. So all these are considered in characterizing the bitumen. And when the properties have been measured, they are related to pavement performance, specifically cracking and rutting. And so when that is done, then we will be sure that a binder with a given PG or performance grade is expected to perform similarly in different conditions. So it does not matter where that binder will be used. If it has a given or a certain performance grade, we expect that it will perform similarly in that environment. So it's a robust system, and this is a typical notation of the SuperPave binder grade. So this is just an example. So we have PG 64 minus 22. Those are the temperatures. The PG is the performance grade. 64 is we call it the high temperature grade. It indicates the highest temperature that this particular asphalt binder will be able to resist rutting. And the minus 22 is the low temperature grade, and it indicates the minimum temperature in degrees Celsius that the binder will be able to resist thermal cracking. And thankfully, we don't have problem with thermal cracking in our part of the world because of our hot climate. So the figures 64 and minus 22, as I said, is an example. You can go in 6 increments. It can be PG 70 minus 22 and so forth. All right, so these figures, the temperatures 64 and minus 22, how are they determined? They are determined by analyzing air temperature data. And typically we want temperature over a long period of time, not less than 20 years. And the temperature data will be summarized into statistical values, and they will be incorporated in models to come up with those figures that you see on the screen, the 64 and the minus 22. So it is kind of a little bit laborious to go through the process. But what we have done is that together with my team, we have analyzed 42 years of data in Ghana, and we have tested several models for determining the binder grades. And out of this work, which we got published, out of this work, we have proposed a superfill binder grade selection manual to facilitate the implementation of the PG binder grading system, which currently is undergoing approval process in the ministry. All right, so now let me move on to the mixture aspect. What kind of innovations we can begin to think about, we can begin to discuss to improve the performance of our asphalt pavement, especially on our high volume routes, All right, so let me talk about a type of mixture we call stone matrix asphalt. Stone matrix asphalt, SMA. This type of mixture was invented in Germany in the 1950s. And at that time, the motivation was to have a very tough surfacing material that will resist the damage caused by started snow ties. And so we have this man, Ziegler, who came up with that misdesign philosophy. And the idea is that it has large coarse aggregate component. And it is a gap gradation, meaning that the mid-sized aggregate particles will be missing. And the coarse aggregate, which comprises 70 to 80% by weight of the mix, will be filled in by the mastic. And the mastic comprises the filler, fine aggregate, binder, and then stabilizing additive if it is needed. All right. So this is his concept of the stone matrix asphalt, design concept, and it worked. It really worked to, reduce the damage caused by started vehicle ties. So on the screen, you should see how the aggregate in a stone matrix asphalt will look like. So you see that there's a high concentration of the coarse aggregate, and the coarse aggregates are in contact with each other. So we call it stone-on-stone contact. So SMA has stone-on-stone contact. And the typical dense graded asphalt mix that we produce and lay in Ghana is what you see on your right. So you see that there is a kind of a uniform distribution of all the aggregate types, aggregate sizes, the large, the mid-size, and then the fine aggregates, right? So this is how the two mixes will compare. So on this plot, I have a typical gradation of the SMA that is in the red. And then I'm also showing the typical wearing mix that we construct. So you see that what we do is dense graded. We see that smooth curve. And that compares with the SMA, which we can see that there's some of the aggregate sizes are missing, and that's the flat part of the curve. All right, so what are the benefits of SMA stone matrix asphalt? There are several benefits. So because of the stone and stone contact of the large aggregate sizes, it helps SMA to better resist rotting. And rotting is a major issue that we have in this country. Then the rich mortar, which others want to call it the mastic, it helps to resist cracking, and it helps to improve durability. Then the surface is coarser compared with dense graded what we have. And that provides several benefits, safety benefits, including improving escape resistance, controlling aquaplaning, which is a safety issue, and also minimizing night glare. And it helps to make road markings very visible. And of course, another benefit is that it helps to reduce noise, especially if the road is going through built-up areas, residential areas. So a lot of studies have been done on SMA, and it has been shown that it provides better performance compared with dense graded asphalt. It has longer service life. And so in jurisdictions where they use it, it is a premium mixture that normally we pave on high volume roads and on high stress areas like intersections. All right, so this map, we see how popular SMA is in the US. All the green and the blue shaded states are using SMA. It is even more popular in Europe, where it originated. And so we are trying to develop some local understanding of how the SMA will compare with our typical dense graded mixtures, and we published this material. So we came to the conclusion that in the overall scheme of things, SMA provides superior performance compared with the DGA, which is actually a corroboration of published information. But here we used our local materials and we went through the mid-design process, and we have ascertained that yes, what is published out there also works in our system. All right, so still on asphalt mix design, let me touch briefly on the various mix design methods that are commonly used in the asphalt industry. We have what we call Marshall and then the super pave. Marshall is what we commonly use in Ghana, which was initiated by Bruce Marshall in the late 1930s. It's purely an empirical approach. So the super pave mix design system tried to improve on the Marshall. So one major difference between the Marshall and the super pave is the manner or the mode of compassion. The mode of compassion. Marshall is using impact, all right, impact compassion, while super pave uses gyration. And studies have shown that gyration type of compassion provides effective stimulation of the kind of compassion or densification that happens on field under traffic. So that was a major improvement that was implemented in the super pave system. Another difference is that with Marshall, the mold size, the diameter is just 100 millimeters, and it means that if you are strictly, applying the Marshall design procedure, the maximum size of aggregates should not go beyond 25. So to overcome this problem, the super pave uses most of diameter 150 millimeters, and that allows the design of mixtures that contain sizes up to, for example, 37.5 millimeters. All right. So even though the super pave has improved the mixture design process, still there's room for improvement. And in the North America, where they use super pave a lot, what they have realized is that it's possible that a mixture will be designed to meet all the requirements of super pave, and yet the mixture will not perform as expected in the field. And so some agencies try to change some of the criteria in the super pave. For example, they want to change the voids in mineral aggregates to allow more bitumen into the mix. And when they do that, they have problem with rotting. Others will change it will reduce the bitumen content, and then they'll have problem with cracking while solving the rotting problem. So research continues. And so there's a need for a mix design method that will optimize the mixture performance against several distresses. So we don't want the mix to be performing so well in addressing, for example, rotting, and then cracking will be left out. So currently, the design concepts, that is BMD, balanced mix design. And what is balanced mix design? Balanced mix design is asphalt mix design, and here the key word is using performance tests. Using performance tests. And the performance tests are used to address multiple modes of distress. So we don't want to optimize the mix to handle one type of distress, but multiple distresses that are prevailing in that region where the mix will be paved. And in doing so, we take into consideration the mix aging, the traffic, the climate, and then the location within the pavement structure where the mix will be paved. So it's a more comprehensive approach to mix design, and it's helping to overcome the shortcomings of the super paved system. And so there are four balanced mix design approaches, A to D. And because of time, I wouldn't want to discuss each of them, but the general trend is that as you move from approach A to D, the level of sophistication will be increasing. However, the opportunity to be creative or innovative will increase. And if you look at each of the approaches, you see that there's one word that is running through: performance, 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 performance. So the idea is that we cannot only depend on the volumetric properties like DFA, DMA, air voice, and all those volumetric properties to decide on the kind of mix to pay. We want to now include performance testing to see how the mix is going to perform in terms of cracking, rotting, and any other distress that the agency thinks is the major issue in their area. All right, so on this screen, you see how the various states in the US, they are adopting one approach or the other. And it shows that there's kind of an active research going on. Some states are way ahead of others. Others have started. Others are now in the preparatory stage, and they are in different stages. All right. So this is a new concept that is really catching up very well in the United States. Now, at the heart of balanced mix design is the kind of performance test that will be done. All right. So is it cracking or rotting? So it is cracking. And for the past 5 years or so, there has been tremendous amount of research into coming up with laboratory cracking tests that will predict how the mix is going to perform. So a lot of research has gone on, and several candidate tests have been, recommended. And now in the screen, you see the different states choosing their cracking test method they prefer and utilizing those tests. And these tests, they are not, well, some are complicated, but with the kind of resources that we currently have in Ghana, we'll be able to test some of them. We're able to conduct some of this kind of testing. All right. So in terms of rotting, It's also another distress, which is the structural distress, very devastating to the pavement. So there are a lot of, not a lot, but several candidates test methods, which research have shown that they are effective and they are reliable in predicting the relative performance of the missiles. And you can see that some states are using the HWTT, that is the Hamburg Wheel tracking device. All right. So some of these tests, yes, we need to improve on our testing capabilities, but some we can do something about it currently. All right, so in case an agency will want to implement balanced means design, these are kind of guidelines that will take the agency through. All right, so I have done some, together with my team, I've done some testing. We try to develop kind of a database of how our mixtures are performing in terms of cracking. So we did a test. We took one of those tests and we did a cracking tolerance testing. We want to see how our mixtures will tolerate cracking as a way of understanding how our mixtures will perform. So we took 23 mixtures from projects that were ongoing around the country. We included wearing, binder, and DBM mixtures. And we fabricated 67 test specimens, and we did a calculation, did a testing, did a data analysis, and we came up with a distribution of the cracking tolerance index. All right, so this is a cumulative distribution of the cracking tolerance index. And so on average of the mixture that we studied, the average cracking tolerance index is around 250. But this is just the beginning, all right? So this, we really need to shadow these projects and see how those pavements perform. Actually, this is the kind of benchmarking studies that we need to be doing to develop better understanding of our mixtures. All right, so balanced meal design, there are a lot of resources online. This is a very good resource that costs just some few dollars. And if you get it, you really have a good understanding of the whole idea of balanced meal design. The last aspect of my presentation, I'm going to touch briefly on the pavement structure design. Historically, we've been using empirical, right? So from the 1920s or even earlier than that, we're using empirical up to when we started doing road tests. And the mother of road tests, as we know, is the actual road test. And that gave birth to the actual pavement design guide. And so in Ghana, our pavement design guide is based on the actual one, and it's purely empirical. But the pavement community has moved on to what we call mechanistic empirical design, with the Asphalt Institute coming up in 1970 with their design guide. Shell came out, and now a popular one is the Ashtoware, the Ashtoware pavement MEE. All right, so there are benefits of mechanistic empirical design. I don't have much time to delve into all this. I will just summarize it. But the point is that in mechanistic empirical pavement design, whilst empirical is just based on experience, right? There's not much use of mechanics theory. Empirical pavement design will consider the pavement as a structure. So stresses and strains will be computed due to application of traffic load. And these pavement responses, the stresses and strains, will be used. So the strains and stresses are used to predict pavement performance. And one advantage of mechanistic empirical design is the fact that the designer can be specific, can target a particular distress. So for example, they can say that, hey, I want fatigue cracking to cover just maximum 20% of the wheel path area. I don't want rat depth to be more than 25 millimeters. Then the pavement structure and the materials to be selected to meet this design requirement. So it's very flexible, of course, because it's robust. It's also a bit expensive in terms of building the models, characterizing the materials, but the payoff is good because we're able to handle the pavement design in a more effective approach. Correct. All right, so basically this is how the ME design concept works. It's very simple. We have the materials. We know that materials will be affected by climatic factors. All that are considered. We put traffic load on the pavement. We will calculate responses. and the responses, that the stress and strains will be developed into damage, and then that will reflect in the form of distresses. So if the distresses that we are going to experience is not what we want, then we change the pavement structure or we change the material properties, and the cycle will be repeated. So this is how it works. This is how the algorithm works. All right, so in summary, let me provide some few suggestions. With respect to super paved binder grade, I want to suggest that we try and get the guidance document out there to guide the industry. We need to provide training, very important, and we need to be doing further research. The SMA is a web probing technology, and we want to take it a little bit further from the lab and maybe construct a test session and compare with what we already know, the dense graded. Then we begin to understand how it works in our environment and how we can develop specifications. I worked in Tanzania about 3 years ago, and they have started doing SMA. And then the balanced mid design, we can adapt the 8-step implementation plan that I showed. MG design is a big one. We need to sensitize stakeholders for them to know the relevance of it. And then we begin with our material and traffic characterization. We have Azure load database. We can start with that. And then we can start delving deeper into it by developing our prediction models. So this is all that I have for you. And thank you so much for your time.